So, at the start of lecture today, I forgot to start recording the meeting. So what I'm doing here is I'm basically going to go through the same set of slides with the same explanations, and I hope that this serves as a more than adequate substitute for the recording of the actual lecture. Please do not hesitate to ask any questions about this. If you think that there's anything I say in this that contradicts what I said in the lecture, please let me know what you think is going on, and I'll do my best to answer your question. But let's start up. And today's lecture is going to be on work and energy and understanding what they are in the physics definition. So let's get started, but before we get started, if you are viewing the recording of this lecture, if you weren't able to attend lecture at the beginning, I want to point out that JMU, in principle, might resume in-person classes, but they have left it up to the professors to decide whether or not a class will return to being in person or remain entirely online for the balance of the semester. I was never comfortable with the social distancing in the classroom in which the class was held, and because of that, I am choosing the option to have this class remain entirely online for the balance of the semester. I hope you understand my rationale, and I hope that this is not a major issue for you. I am sorry if it is, but I think that this is in the best interest, the best long-term interest for everybody. Now let's get started on the physics material, and we start by looking at the concept of work. But we have to be really careful about understanding the physics concept of work because it might not be the same as your basic, your immediate understanding of what I mean when I use the word work. Because when we talk about work in everyday lives, we talk about the work that we've done. If you talk about, I worked 8 hours in the office and I worked 2 hours at home. Wow, I worked 10 hours today. But that's not necessarily the important thing from your boss's perspective. Maybe on that day, you were working to create a report, and you create a 40-page report over the course of the day, but then you decide, there's about 12 pages here that I can remove. I really don't need these 12 pages. They're not essential for the boss to understand. They're not essential for decision-making, whatever. So you're down to 28 pages. You've done enough work for 40 pages, but the finished product is 28 pages. And that's what your boss cares about. Your boss isn't going to look, wow, you did 40 pages worth of work. No, your boss is going to say you turned in a 28-page report. We look at the work done on the product, on the thing of interest. Not the amount of effort that you expend, but the actual results of the effort that you expend. So it is slightly different. And to help understand that slight difference, let's consider a hockey puck moving over an icy surface, a horizontal icy surface. By making it icy, the friction becomes pretty negligible. So we just have this hockey puck on this horizontal frictionless surface. And if you think about that, and you think about prepositions, if you've ever studied a foreign language, one of the worst things about any foreign language are the prepositions. You use the word from or of or in or on or with or about. Prepositions are complicated, and they convey very important distinctions, and this is one of them. We talk about work, we are talking about the work done on an object. We are not talking about the work done by the thing doing the work. We talk about the effect it has on the object, the work done on the object, not the work done by the agent that is pushing the the object or pulling the object. So, like it says, if you push a heavy box across the floor, I don't care how tired you feel at the end. The only thing we worry about is what changed about the box. If nothing changed about the box, you did no work on the box. It's like trying to push on a wall. If you push and push and push on a wall, unless you're Superman, that wall isn't moving. You've done zero work on the wall, no matter how tense and tired your muscles feel. In this context, we look at work as being equal to force times change in displacement. So if we imagine our hockey puck on this nice horizontal surface, so we see the profile of the hockey puck, we exert a force on the hockey puck, and while we are exerting that force, we keep pushing on that hockey puck, and it moves a distance across the ice. We're going to refer to that distance as a change in displacement. And the work that is done is equal to the force times the change in displacement. And I'm using change in displacement and I'm using force because I want to point out the directional nature of force and the directional nature of change in displacement. Both of those are vector quantities, and their relative directions are very important in determining the work done. Let's discuss that. If I talk about delta x instead of just plain old distance, if I talk about change in displacement, does that mean, now since change in displacement could be positive if the object moves to the right, change in displacement is negative if the object moves to the left, if change in displacement could be positive or negative, could work be negative? And the answer is yes. It is possible for the work done on something to be negative. Work might be positive, work might be negative. How do we know? And let's not overcomplicate this. You determine whether or not the work is positive or negative by the relative directions of the change in displacement and the force. If both are in the same direction, the work is positive. If they are in opposite directions, the work is negative. That's it. You just have to, in given a problem, you have to visualize things. For instance, there's a homework question that is due this coming Friday. And in the question, you are given a force and you are given a direction in which the force is acting. You are also given an initial displacement and a final displacement. So to go from the initial displacement to the final displacement, you have to figure out in which direction the object must move. The direction the object moves to go from the initial to the final displacement is the direction of the change in displacement. So you're told the direction of the force. You have to figure out the direction of the change in displacement. And then you have to ask, are these in the same direction or are they in the opposite direction? If they're in the same direction, the work is positive. If they're in the opposite direction, the work is negative. So that is all that you need to consider in determining if work is positive or if it's negative. Let's first do a quick numerical example. We have a goalie who is pushing a hockey puck. The goalie applies a force of 32 newtons, and in the process of applying that force, they apply it over a distance of 0.64 meters, at which point the puck leaves contact with the stick, and so there's no longer any force acting on it. So 32 newtons over a distance of 0.64 meters. What is the work done? This is as simple a work-related question as you could hope for. You're given the force, you're given the change in displacement. If you visualize the problem, you'll see that the force and the change in displacement are in the same direction as the goalie tries to pass it to a teammate or something. And so F is 32, delta X is 0.64. 32 newtons times 0.64 meters gives you 20.48. And then you see I've written this capital J. Capital J, that represents the units of work. It stands for joules. And let me discuss that in a little bit more detail here. We have the expression work is equal to force times change in displacement. Well, force has units of newtons, and change in displacement has units of meters, so it stands to reason that units of work is equal to units of force times units of displacement. It must be equal to newtons times meters. At a more foundational level, a newton, which goes as m times a, mass times acceleration, a newton is equal to a kilogram times a meter per second squared. So the units of work are equal to the kilogram times the meter per second squared times meters. Or, if we simplify things a little bit, the units of work in its most basic combination is kilograms times meters squared per second squared. This combination, though, kilograms times meters squared per second squared, has been renamed the joule, capital J-O-U-L-E, pronounced like the gem, but spelled differently, the joule in honor of James Prescott Joule. As you can see, he was an English scientist who put the final nail in the coffin of phlogiston theory. Phlogiston theory was an idea about the nature of heat and burning things. And by the time Joule did his work in the early 1800s, he finally solidified that the phlogiston theory is completely incorrect, and it was just tossed by the wayside. No more phlogiston theory. It was abandoned. The Joule named in honor of him. Now, I said that you can determine whether work is positive or it's negative simply by asking, are the work and the change in are the force and the change in displacement in the same direction, or are the force and the change in displacement in opposite directions? Take a look at this question. We have an object that is falling to the ground. Maybe it was in your hand, it slipped out, it's falling to the ground. While it's falling, the work done by the gravitational force, is it positive? Is the work negative? Or is it zero? Ask yourself, while it's falling, what is the direction of the change in displacement? And what is the direction of the gravitational force? Once you've determined those, the next question you ask is, are they in the same direction or are they in opposite directions? If they're in the same direction, you say the work is positive. If they're in opposite directions, you say the work is negative. And I hope that you are coming up with positive. Gravity is directed down. The object is moving down, so its change in displacement is down. Since both are down, both are in the same direction, the work is positive. Another way you can recognize this is that the object is moving down and, well, the object is speeding up. Just simply that. As an object falls, it speeds up. If the object is speeding up, the work done on it is positive. On the other hand, imagine you toss an object up into the air. The object is going to move up, and then it's going to move down, but only consider the motion while it's moving up. What can we say about the work done by the gravitational force? Is it positive, is it negative, or is it zero? So again, you ask yourself the question, what is the direction of the change in displacement? What is the direction of the force? Are they in the same direction or opposite directions? Once you've come to the end of that third question and answered it, you should be able to tell whether the work done is positive or the work done is negative. Hopefully, in this question, you came up with negative. While that object is moving up, the gravitational force is still down. So the change in displacement and the force are in opposite directions. The work is negative. Furthermore, as the object is moving up, it's slowing down. If the object is slowing down, the work done on it must be negative. So we have a couple of reasons why to say that the work done on the object while it's moving up is negative. So as I pointed out, if you do work on an object, it's done to speed it up or slow it down, but its speed is going to change. If the force is if the direction of the force is the same as the direction of the change in displacement, the object is speeding up. If the force is opposite to the change in displacement, the object is trying to slow down, but the object speed is changing. And that's going to lead us to a more quantitative way to understand the nature of work. We are going to look at a property that is strictly associated with an object. Now, this property is associated with the object and the motion of that object. And what we want is a property that is directly related to work. So, if I do work on an object, I change this property of the object by exactly that much work. And this property is called kinetic energy. Kinetic energy is, the energy associated with motion. Kinetic means moving around. I'm not going to hold you responsible for the derivation of the formula for kinetic energy, but it is what it is so that it is consistent with our definition of work. And it has this seemingly extraneous factor of 1/2 in it, but without that 1/2, everything would collapse in a heap. This is the result of the derivation. Kinetic energy must be equal to 1/2 mv squared if we want to hold on to work being equal to force times change in displacement. So here's this property of an object, kinetic energy. All objects have kinetic energy because all objects that you know of have a measurable mass and a measurable speed. So if you know their mass and you know their speed, you can do 1/2 mv squared and you got the kinetic energy of that object. Kinetic energy is specifically designed so that it has exactly the same units as work. Units for kinetic energy, the joule, abbreviated as a capital J. Okay, a lot of text. Take a breath. Okay, that was enough. Kinetic energy equals 1/2 mv squared. M is always greater than 0. It's always a positive quantity. V, the speed, or the velocity, really. The velocity could be either positive or negative, but it gets squared. If I take a positive number and I square it, I have a positive number. If I take a negative number and I square it, I have a positive number. So V squared, no matter what, is always positive. So N is positive, V squared is positive. Kinetic energy is always positive. The only time it isn't positive is when it's exactly equal to 0. The only time that happens is if the object is motionless. So if all objects have a kinetic energy. It might be 0 if it's not moving. But if it is moving, then it's guaranteed to be greater than 0. Kinetic energy has no direction. There's no such thing as kinetic energy to the left or to the right or up or down. It has no direction. And that leads us to the reason why we developed this concept of kinetic energy. Remember, I said that we wanted a property of an object that would be directly affected by the work done on the object. So if I do so kinetic energy is defined such that if I do 50 joules of work on an object, that object's kinetic energy increases by 50 joules. If I do negative 50 joules of work on an object, then that object slows down. Its kinetic energy changes by negative 50 joules. Its kinetic energy decreases by 50 joules. So the net work done is equal to the change in kinetic energy. That's how kinetic energy is defined. And in a more convenient equation format, we would say that the net work is equal to 1/2 mv final squared minus 1/2 mv initial squared. I should point out, in this class, you will not have to worry about the mass changing. That is literally rocket science. We are only going to worry about the speed changing. Any object that is moving in this class is going to have a fixed mass. It is not going to change. The only thing that will change is the speed, v. So if you know the final speed and you know the initial speed and you know the mass, you can calculate the change in kinetic energy, and in turn, you could calculate the net work done on the mass. This, by the way, is called the work energy theorem. It is a theorem. It's a physics theorem. It's the only theorem I'm going to really throw at you in this class, but hopefully, despite the fact that it has a rather intimidating name, I hope that the logic behind this makes sense to you, I hope that that formula on the previous slide makes some sense to you. Now, I want to discuss work energy theorem in a little bit more detail. I want to make sure that we understand it because it goes a little bit against what your everyday understanding might be. You might have had some experience pushing a heavy object across the floor, and you're pushing really hard on that object, and that object is neither speeding up nor slowing down. I want to make sure that you understand the concept of what we mean by net work. Net work is the total work done by all the forces. Take the work done by each force, add them all up, that gives you the total work. A force that you encounter when pushing a heavy object across the floor is friction. We didn't worry about it with the hockey puck, but in many situations in real life, it's a very real thing. If you are pushing an object across the floor, let's say you are pushing to the right, friction is opposing you. Friction is to the left. Now, you might have, it does take some force to get this object moving in the first place, but let's consider from the time this object is already in motion. Not the initial extra heavy push to get it started, but you're applying enough force to keep it moving. And let's say you're pushing this across the floor at constant velocity, same speed, same direction. The acceleration of the object is zero. Now, if the acceleration of the object is zero, one of the things that should tell you is, from Newton's second law, the net force is also zero. So if the net force is zero, then the net work is zero. If the net work is zero, the object is neither speeding up nor slowing down. Net work of zero means the kinetic energy is not changing. So if this object is moving already to begin with, and it keeps moving with a constant velocity, a constant speed, then the work done during that portion of its motion, the net work is zero. You are doing positive work, you are trying to speed it up to the right, but friction is opposing you, it's trying to slow it down, friction points to the left. The net effect is that they cancel each other out, and the net work during this portion of the motion is zero. Now, a couple of example questions. First one is relatively simple. I could have made it a bit simpler, but this is still not too bad. 15.5 kilogram object has a kinetic energy of 59.2 joules. What is the speed? Now, this problem could have been simpler if I gave you the mass and the speed and said, what is the kinetic energy? If I give you n and v, you plug into 1/2 mv squared, you get the kinetic energy. But here I gave you the mass and the kinetic energy, and I'm telling you to solve for v, the speed. And so that's going to take a little bit of algebra. If I were you, I would pause this video and start with the expression kinetic energy equals 1/2 mv squared, and see if you can solve on your own algebraically for v. So pause now. And we're back. So what does that look like? kinetic energy equals 1/2 mv squared. I multiply both sides by 2. I divide both sides by m. I take the square root. Algebraically, v, the speed, is equal to the square root of twice the kinetic energy divided by mass. So I do 2 times the given kinetic energy of 59.2 divided by the mass of 15.5 kilograms. I do that calculation, and then I take the square root of that resulting number. Don't forget to take the square root. I guarantee you that if this were a test question, one of the wrong answers would be from forgetting to take the square root. But if you take the square root correctly, you should get the correct answer of 2.76 meters per second. So 15.5 kilogram object moving at 2.76 meters per second has a kinetic energy of 59.2 joules. The second question, now I didn't get to the second question during today's actual lecture, but I'm going to cover it here in this recording. The second question we have, and I will discuss this at the start of the actual class lecture next time. A 12.9 kilogram mass has a speed of 7.11 meters per second. But then something comes along and does negative 223 joules of work on it. And the question is, what is the final speed? We see that work is explicitly mentioned. We see that speed is explicitly mentioned. That's a pretty good clue that there's going to be the work energy theorem. That's what you'll want to start with. If we look at the work energy theorem, net work equals 1/2 mv final squared minus 1/2 mv initial squared. The unknown quantity is v final, the final speed. We know the net work, we know the mass, we know the initial speed. If we want to solve for the final speed, I can first take the work energy theorem and algebraically revise it just a little bit. 1/2 mv final squared equals the net work plus 1/2 mv initial squared. I know everything on the right-hand side. I can calculate everything on the right-hand side, and what I get is, on the right-hand side, is 103.06. So 1/2 mv final squared must be equal to 103.06. I know the mass, I know the kinetic energy. I want to find that speed v final in this case. And look, just like in the first example on this problem, I have to do 2 times the kinetic energy. 2 times the kinetic energy divided by the mass. In this case, the kinetic energy is 103.06 and the mass is 12.9. And I got almost exactly 4 meters per second. I got like 3.997 meters per second when I did it on my calculator. So basically 4 meters per second. The object started at 7.11 meters per second. I expect it to slow down if I do negative work. That tells me my final answer better be less than 7.11. Has to be between 0. Can't be less than 0. Can't be greater than 7.11. I got 4. That makes me satisfied. One last comment. I don't want to throw a lot of equations at you. Today we had the equation for kinetic energy, we had the equation for work, and we had the work energy theorem, the equation that relates work and kinetic energy. And it'd be nice if I could go through an entire class without touching math, without touching equations. But as you know, I liken it, as you can see on the screen. You can take an Olympic sprinter like Usain Bolt on the left, and you can bound him up like you see Hannibal Lecter on the right, and ask him to do a 100-meter dash. I trust Bolt to somehow be able to get to the end, but it's going to take him quite a bit longer than 10 seconds, I'd bet. Anyhow, that's all I got for this, so I'm going to stop the recording here. Please accept my apologies for not having recorded the actual lecture, but this is basically the material that we covered.